Welcome to ATMOS 5000, day 15. Our objectives today are being pulled from the Stull textbook, Chapter 5, sections 5.6, 5.7, and 5.8. Specifically, we're going to talk about buoyancy in the atmosphere, and we'll define a Brunt-Vaisala frequency and period for buoyancy oscillations. We'll introduce the concept of atmospheric stability, dividing the atmosphere up into stable, unstable, neutral, and conditionally unstable conditions. We'll figure out how to determine the tropopause height, and we'll also try and figure out how to get the mixed layer depth, which is the depth of the boundary layer. Recall that force is equal to mass times acceleration. So if you divide both sides by mass, you'll get acceleration is equal to force divided by mass. So what we're looking at here is the buoyancy acceleration, which is the buoyancy force divided by the mass of the object. And we have several different ways to calculate this. The most straightforward is just using the density of the air parcel minus the density of the environment divided by the density of the parcel. And that gives a unitless parameter, which is multiplied by gravity to get the buoyancy acceleration. You can do the same thing with the virtual temperature of the parcel minus the temperature of the environment, or you can use the temperature of the parcel minus the temperature of the environment, or the density of the or the potential temperature of the parcel minus the environment, or the virtual potential temperature. All of these will give a fairly accurate representation of the buoyancy. So these buoyancy acceleration results from density differences, and I love the picture on the left because it's basically very carefully somebody has put in fluids of different densities and has used dye to help demonstrate to where those fluids are located. And then they've dropped objects of different densities, and some of these objects are clearly sitting on top of layers of fluid in there. And it really just shows the effect of density has on buoyancy of an object. Objects that are more dense than their surroundings will sink, and objects that are less dense than their surroundings will rise. The Brunt-Vaisala frequency and period is essentially a measure of the stability of the atmosphere. So in the picture down below, we actually have a mountain obstruction, and the air is being pushed up over that obstruction. And in the case of a stable atmosphere, that is going to cause waves to form downstream of that object. And the Brunt-Vaisala period or frequency is essentially a measure of these waves, and it'll give their period and their frequency. It's defined as the square root of gravity divided by the virtual temperature times the gradient of the virtual temperature plus the dry adiabatic lapse rate. Or you can also do this in terms of the virtual potential temperature, where the Brunt-Vaisala frequency is the square root of gravity divided by the virtual temperature times the vertical gradient of the virtual potential temperature. The period of the Brunt-Vaisala frequency is essentially 2 pi divided by the Brunt-Vaisala frequency. We're going to start off with the following 3 stability definitions. We're going to start off with stable, unstable, and neutral. For an object to be stable, if you displace it, it will return to its original location. So you can often think about this as a horizontal displacement or a vertical displacement. The actual stability doesn't matter. It only matters whether or not the object returns to its original location. For an unstable situation, an object that is displaced will accelerate away from its original location. And for a neutral atmosphere, in this case, an object that is displaced will remain in its new position when the displacement force ceases. So here we happen to have a marble that is in a basin, and we're going to flick that marble and watch its behavior. So in this case, we displaced the marble away from its original location, and what did it do? It returned to its original location, so that by definition is going to be a stable condition. Let's take this example. We have the marble, it's on the edge of the basin, and we're going to nudge it toward the basin, and we'll see the result of what happens. So in this case, a small displacement actually caused the marble to accelerate away from its original location, and it did not return. And so that, by its definition, is an unstable situation. Here we have our marble. It happens to be on a flat surface, and we're going to nudge it and then stop it and then see how it behaves. So we pushed it, we stopped pushing it, friction or whatever else stopped it, and then it remains at the location where the forcing stopped. So in that case, we have what we refer to as a neutral atmosphere, or neutral situation. So what factors control the stability of the atmosphere? It's one thing and one thing only, and it's the environmental lapse rate. The environmental lapse rate, recall, is defined as minus the change in temperature divided by the change in height. And we usually do this in terms of degrees Celsius per kilometer. So here we're going to determine the atmospheric stability through a series of cases. This happens to be case number 1. Recall that you measure the environmental lapse rate using a Raywinson balloon, and so that is denoted here by the round circles and the red line connecting it. So we go out on this particular day and we launch a balloon, and it happens to measure the temperature of the environment, and it happens to be isothermal, which means that the temperature is not changing with height. So next, we grab an air parcel at the surface. The air parcel is going to be denoted by the blue square. And then we lift that air parcel, and because it's a dry air parcel, it's going to decrease at the dry adiabatic lapse rate, or about 9.8 degrees Celsius per kilometer, so that by the time this air parcel reaches 2 kilometers, it's almost 20 degrees Celsius colder and has a temperature of almost 0 degrees Celsius. In this situation, compare the temperature of the air parcel to the temperature of the environment at that altitude, and you'll see that the air parcel is much colder than the environment. So in this case, the air parcel is colder than the environment. Does that mean that the air parcel is more or less dense than the environment? Well, if it's colder, it's going to be more dense. And now, if the air parcel is more dense than its surroundings, will it rise, sink, or remain stationary? It will sink. And because we lifted this air parcel from the surface, we forced it upwards, we let go, and it will sink. It'll sink all the way back down to its original location. We're going to refer to that as a stable atmosphere. So, is the atmosphere stable, unstable, or neutral? Stable. Here we have case 2. The only thing that's going to be different in this example is the temperature, or the environmental lapse rate, as measured by the Raywinson balloon. So we launch our balloon, it was still 20 degrees at the surface, but now it's 10 degrees Celsius at 2 kilometers. and that defines our environmental lapse rate. Once again, we lift our air parcel, and it follows the dry adiabatic lapse rate, and we can cycle through the exact same questions that we had before. Is the air parcel colder or warmer than the environment after it's been lifted? It's still colder. Is it more or less dense than the environment after it's been lifted? It's going to be more dense than the environment. And will it rise, sink, or remain stationary? Well, because it's more dense than its surroundings, it's going to sink. Is the atmosphere stable, unstable, or neutral? Well, because this air parcel is going to return back down to its original location, it's still going to be stable. So let's take case number 3. In this case, we have a ray-wind-son balloon that's launched. It's still 20 degrees at the surface, and now it's essentially 0 degrees at 2 kilometers. We take our same air parcel, we lift it dry adiabatically, and it just so happens that at that altitude of 2 kilometers, the air parcel and the environmental temperature are exactly the same. So is it colder or warmer than the environment? It's the same. Is the air parcel going to be more or less dense than the environment? It's going to be the same because they have the same temperature and same pressure. Will the air parcel rise, sink, or remain stationary? Well, because the density of the air parcel is the same as the environment, there's no buoyancy acceleration, so it will remain stationary. And so is this an example of the atmosphere that's stable, unstable, or neutral? Well, you lifted the air parcel. When you removed the forcing, brought it to a standstill, essentially it is remaining where it's at. That, by definition, is going to be neutral. So case number 4, a different day, we launch a different balloon. This time the ray-wind-son balloon, the temperature decreased rather quickly. It's all the way down to minus 5 degrees Celsius at 2 kilometers. In this case, we take our air parcel, we lift it dry adiabatically, and now we can answer our questions once again. Is the parcel colder or warmer than the environment? It's going to be warmer than the environment. Does that make it more or less dense than the environment? Less dense. Will this air parcel rise, sink, or remain stationary if it's less dense than the environment? It will rise. Is this an example of a stable, unstable, or neutral environment? Well, because any nudge of that air parcel vertically, it's always going to be warmer than the environment. It's going to spontaneously rise and accelerate away from its original location. Therefore, this is going to be an example of an unstable situation. And the last case is a temperature inversion. We get these a lot during the winter here in Utah. And we're going to once again do our thought experiment with our air parcel, lifting it dry adiabatically to 2 kilometers. And now you can see that there is a massive temperature difference between our air parcel and the environment. We can walk through our thought process again. The air parcel colder or warmer than the environment? Much colder. Is the air parcel more or less dense than the environment? Much more dense. Will the air parcel rise, sink, or remain stationary? It's going to sink. Is the atmosphere stable, unstable, or neutral? Very stable. And the only difference in all 5 of these different cases was the environmental lapse rate. And so by just looking at the environmental lapse rate, you can instantly determine the stability of that layer of the atmosphere. So let's extend this to a moist air parcel that will be undergoing both dry and moist convection. So here we launched our ray-wind-son balloon. That's our red circle and red line again. And we lift our air parcel up using the dry adiabatic lapse rate until we reach the lifting condensation level. And beyond that, it's going to be following the saturated adiabatic lapse rate. So in this case, it's going to be absolutely unstable because the air parcel is always warmer than the environment. It doesn't matter if it's 10 feet off the ground or 2 kilometers off the ground. The air parcel in this case is going to be warmer than the environment, which makes it accelerate away from its original location. Case 2. We once again have a Ray-Winson balloon launch that happens to decrease at about the dry adiabatic lapse rate. So our air parcel will be lifted up to 1 kilometer, where it will become saturated, and then it follows the saturated adiabatic lapse rate. And we're going to refer to this situation as conditionally unstable. Why is it conditionally unstable? Well, the atmosphere below the lifting condensation level in this example is neutral because the air parcel has the same temperature as the environment. But in this example, once you hit the lifting condensation level and move beyond that, the air parcel is going to be warmer than the environment, which means that it's going to spontaneously rise and it will become unstable. So in this case, the atmosphere is stable, in this case neutral below the lifting condensation level and unstable above. And the condition is that the air parcel has become warmer than the environment, in this case at the lifting condensation level. That normally happens at the level of free convection, but in this particular example, it happened at the lifting condensation level. So here we launch a balloon and we have yet a different environmental lapse rate. And in this situation, you lift your air parcel from the surface. It follows the dry adiabatic lapse rate to 1 kilometer. And at 1 kilometer, which is the lifting condensation level, the air parcel is still colder than the environment. And it would, if you let go at that point, it would fall all the way back down to the surface, and that would be stable. But if you continue lifting your air parcel beyond about 1.25 kilometers, the air parcel becomes warmer than the environment and will become unstable. So we define that crossover point as the level of free convection. And the atmosphere here is considered conditionally unstable because the atmosphere is stable below the level of free convection, and the atmosphere is unstable above the level of free convection. And this is the most common situation or stability classification for the atmosphere, is a conditionally unstable atmosphere. And for case number 4, we have an air parcel, we have a environmental lapse rate that is shown here. Its temperature is only decreasing slightly with height. And on this situation, it doesn't matter whether the air parcel is below cloud base, below 1 kilometer, or above cloud base, above 1 kilometer. Everywhere, this air parcel is colder than the environment. And therefore, if you let go at any one of these points, it's going to be more dense than the environment, and it's going to sink all the way back down to the surface. So this is an example of an atmosphere that is absolutely stable, because the air parcel is always going to be colder than the environment. And here you have another example. This would be a conditionally unstable atmosphere. It will be stable below the level of free convection. That crossover point is about 1.1 kilometer. And it will be unstable until it reaches about 2 kilometers. And at 2 kilometers, we have the equilibrium level. And if the air parcel were to continue above the equilibrium level, it would now be colder than the environment and would be stable and would return back to the equilibrium point at 2 kilometers. So we have our lifting condensation level, our level of free convection, and our equilibrium level all defined in this scenario. What's the stability below the level of free convection? It's going to be stable because the air parcel is colder than the environment. What's the stability of the layer between the level of free convection and the equilibrium level? It's going to be unstable because the air parcel is warmer than the environment. And what's the stability up above? Well, the air parcel is going to be colder than the environment, so it's going to return back down to its equilibrium level. So that is going to be a stable atmosphere again. And once again, the only thing that you needed to know in order to be able to determine the stability of the atmosphere is the environmental lapse rate, which is measured with our Raywin-Sum balloons. So to summarize the static stability of the atmosphere, the only thing we need to know to determine the stability of the atmosphere is the layer environmental lapse rate. And we have to compare that lapse rate to the saturated adiabatic lapse rate and or the dry adiabatic lapse rate. And recall that the lapse rate is defined as negative delta T over delta Z. So the atmosphere is absolutely stable if the lapse rate is greater than the saturated adiabatic lapse rate because the air parcel is always going to be colder than the environment. The atmosphere would be considered saturated neutral if the environmental lapse rate is equal to the saturated adiabatic lapse rate. We did not do an example of that. It would be conditionally unstable if the atmospheric lapse rate is between the dry adiabatic lapse rate and the saturated adiabatic lapse rate. It would be dry neutral if the lapse rate is equal to the dry adiabatic lapse rate, and it's going to be absolutely unstable if the lapse rate is less than the dry adiabatic lapse rate. So think about this. The dry adiabatic lapse rate is defined as minus 9.8 degrees Celsius. So a environmental lapse rate that is less than that would be minus 10 or minus 11 or minus 12 degrees Celsius per kilometer. So finding the tropopause. Here we have a skew T diagram that has the temperature from the Raywin-Sum drawn in red and the dew point temperature drawn in blue. And the temperature at the tropopause will typically become isothermal over a deep layer. And so here we have an example up near the top of the chart above about 15 kilopascals where the temperature abruptly becomes isothermal. Recall that on the skew T diagram, the temperature, the isotherms are constant and move up to the right at a 45-degree angle. So in this case, we have an isothermal atmosphere up high, and that is the base of the tropopause. In this particular example, we have smaller temperature inversions which exist. They're typically not particularly deep, and the tropopause will typically be at pressures less than 40 kilopascals. So if you see a temperature inversion at 50 or 60 kilopascals, that is very unlikely to be the tropopause. And then identifying the boundary layer is often very difficult, and we will look at as many parameters as we can to try and identify the layer of the atmosphere that is being influenced by the surface. So for example, we often will look for a capping inversion. We'll look for the wind direction shifts. We'll look for an increase in the wind speed. Both of those will happen as you move away from the surface because there's less friction with the surface. Will cause the wind speed to increase and will often change direction. We can often have a dew point change because we have a different air mass. And a lot of times the temperature below the inversion will be nearly adiabatic in the afternoon because of vertical mixing. And that basically means that the potential temperature is constant with height. So in this example here, if you take a look at the surface, we have a temperature which is decreasing at an almost adiabatic fashion. And then we have a isothermal layer extending from about 80 kilopascals to almost 85 kilopascals. And at that location, you'll notice that there is an abrupt change in the wind direction and the wind speed. Mostly the wind direction, though. The wind direction is from 5 knots from the northwest, and it switches to 15 knots from the essentially the west or the west-southwest. And at that same point, the dew point temperature drops as well, indicating the potential of a different air mass above the boundary layer. So on this particular sounding, I'm going to refer to the mixed layer as being that layer that lies below that capping inversion, where the wind abruptly changes at that location, as does the dew point temperature. It's not always so clear, but we will do a lot of examples, and this is often easier to see in the afternoon sounding, or alternatively, if you have a temperature inversion at the surface, it's often easy to see that at night as well.